Okay, semi-classical approach. Let us assume that a given atom, initially raised to its excited level 2 of energy E2, is decaying by spontaneous emission to level 1 of energy E1. We will assume that the two levels are non-degenerates and solid psi1 R comma T is equals to U1 R exponent negative J into E1 over H bar times T. And for level 2, psi 2 on R1T is equals to U2 R exponent negative J into E2 over H bar times T. Here for level 2. For level 2. B. The corresponding wave functions where U1 and U2 are the eigenfunctions of the two stationary states are denotes the coordinate of the electron undergoing the transition, the origin being taken at the nucleus, and H bar is equal to H over 2 pi. When the atom is undergoing the level 2 to level 1 transition due to spontaneous emission, its wave function can be expressed as a linear combination of the wave function of the two states, that is psi is equal to A1 at T of psi 1 plus A2 at T2 at T psi 2, the general equations for these transitions. The combination of these two energy levels, that is for psi 1 and for psi 2, that's the combination of these two psi 1 and psi 2 gives here the sum of psi, where A1 and A2 are time dependent complex numbers. A1 and A2 are time dependent complex numbers. Time dependent complex numbers. Note that according to quantum mechanics we have here absolute value of A1 is square plus absolute value of A2 is square is equals to 1. The magnitude gives 1. And thus A1, the magnitude of, and thus magnitude of A1 square and magnitude of A2 square represent the probability that at time t the atom is found in state 1 or 2 respectively. To understand how spontaneous emission arises, let us calculate the electric dipole moment of the atom mu according to quantum mechanics. We have here mu, which is the electric dipole moments of the atom, mu, which is equal to negative integral of E and the absolute value psi square, the magnitude of psi square r dV. This is the electric dipole, moment of the atom.